All right, so let's take a look at an example, and I call it a friction example, but honestly, it lays out a nice set of principles that we're going to use on a lot of force problems. Okay, very simple question. At what angle will a box break away and move? And the idea here is that we are tilting this surface up and up and up. We're increasing theta until the box here breaks away and starts moving down the incline. Now I've already done the setup, right? I've taken a diagram that probably didn't exist, or maybe if it did exist, it had the incline and the box on it, but no forces. And I've added all the forces, but let's quickly enumerate them. One, we've got the normal force, which we're always going to have when you have two surfaces in contact. And that's perpendicular to those two surfaces. We've got gravity on the box, right? That is always straight down towards the center of the earth, so we've got that. And we've got the force of friction on the box. And we know that that's going to exist, and we know it's going to be up the incline rather than down in this case, because there's no other pushes and pulls. And in that case, you've got some little piece of gravity that acts, in this case, along the x-axis that I've laid out here in coordinate system. And that's going to be opposed. That attempt to pull the box down the incline is going to be opposed by the force of friction, okay, whether that's static or kinetic. Now, the other thing I've done in terms of setup is I've taken my usual XY coordinate system, which normally we have like this, right, where we've got Y vertically and X horizontally, and I have said, nope, I'm going to twist it so that it is aligned with either the parallel to the incline direction, that's for X, or the perpendicular to the incline direction, which is Y in this case. And the reason for that is, one, we're free to do it because coordinate systems are a human invention, not a natural one. And two, it's just going to make the mathematics in this case simpler because we've already got two forces, this one and this one, that are aligned with, my Netflix notification there, if your eyes were quick. You've already got two of these forces, force of friction and force, the normal force, aligned with the X and Y axes, respectively. The only one that's off axis is force of gravity, and we know how to deal with that kind of thing. We can split it into its components, and off we go. So, being asked this question and being given, well, honestly, very little here, okay? The obvious question is, how do we proceed? All right. So let's grab a pen and let's talk a little bit about that, how that might work. Well, we want an angle, and we have some ideas about how we might relate the angle to the forces in this case, because we know, for instance, that this little piece of gravity here that's acting in the positive x-axis is going to be dependent on what this theta is, right? The more you tilt up the incline, the larger and larger and larger a component that is going to be, the one that's along the incline. Because if you imagine you tilt the incline all the way up here so that it's vertical, well, then the entire force of gravity would be in the along the incline. Okay, so we know that this theta is definitely going to tell us about the components of f sub g, both the x and y. So we can pretty easily get a relationship to this angle that we want to find. And then the question is, well, what kind of equation are we going to put that into? And if you're talking about forces, 9 times out of 10, really, you're going to start talking about Newton's second law. And the thing that we're going to do here, we can write that down. We know that F equals ma. Okay. And the question is, okay, well, what's the crucial point? Like, if we're just asking what angle will the box break away and move, we don't know anything about the mass. We know of the forces, but we don't know what the net force is. We don't know what the acceleration would be, all of that kind of stuff. Where do we go from here? Well, we actually do have an idea of what's going on here, right? We're saying that at some critical angle, this piece of gravity, this one right here, that's acting downhill, is going to grow to be bigger than the maximum value of the static friction. So really what we're looking for is the angle where Fs max, so the force of static friction, the maximum value, is equal to the x component of g. And I'll call that F sub g x. Okay, so because that's this thing right there that we've been talking about, that piece of gravity that's trying to drag the thing downhill along the surface. That's what we're really looking for. Because if we tilt it just an infinitesimal amount larger than whatever angle this condition happens at, then we know that it's going to break away and start moving, because this piece will be bigger than this piece. And so there'll be a net force in the positive x direction, and the thing will start accelerating down the hill. So really what we're looking for is that inflection point where these two bits are equal to one another. All right, so that probably means that we're going to have to write down a sum of forces in the x direction, certainly, because those two pieces, this static friction maximum and this x component of F sub g, those exist along the x-axis, negative and positive respectively. So we can come over here and we can write down sum of all the forces in the x direction is equal to the mass of this object times the acceleration in the x direction. And how many different forces do we have acting in the x direction? Well, just two, right? Normal force is all in the y direction, so we can ignore that for now. And so all we have here is, if we replace this sum with the two forces in question, we have some negative force of static friction, so I'll use S for the subscript. And we're going to be summing that with the force of gravity, the x component of the force of gravity, and that has to equal mass times acceleration in that direction. Okay, so we sort of expand that sum to that. Great. All right, and then what is the acceleration going to be? Well, if this condition is actually true, right, sort of this critical angle at which this happens, where if we tilt it up just a tiny bit more, then these will not be equal and gravity will win out and it'll start moving. Well, at that inflection point, though, these two things should balance out. So the acceleration should be 0 until we, just the tiniest little bit, make that theta bigger. So what we've got is that, if I just rearrange this slightly, fgx minus whatever maximum static friction is, okay, is equal to 0. Now, we can figure out both of these things. Let's do the x component of f sub g first. That's going to be mg, and we know it's going to be sine theta or cosine theta, right? And you can work that out from the geometry. Like, you can go through and be like, oh, well, if this is theta, well, then this angle right in here between the parallel to the surface, the x-axis, and the force of gravity is going to be 90 minus theta. And then you can say, well, then this over here is going to be theta. And then you can say, okay, well, then this opposite side is going to be fgx, okay? Might be a little bit small, but I think you get the idea if you're following along. And so we are expecting it to be mg sine of theta, because that side there is opposite to the theta that we intuited our way to through geometry. But why? There must be a simpler way to do that, right? I mean, maybe that's simple to you and you're happy and you'd go and do that way every time, but there must be a simpler way. Well, what would be the horizontal component if we had the block sitting here? What's the horizontal component of f sub g when theta is equal to 0 degrees? Well, that's an obvious thing, right? There's no horizontal component, right? It's down, okay? And so if we take if we take our relationship, our sine or our cosine, and we take theta and we set it to 0, well, then we better come out with a 0 horizontal or x component. And the only function that does that is sine theta. If you put 0 into cosine theta, you get a 1, right? It would tell you that gravity was entirely horizontal. Doesn't make any sense, okay? So whichever way you do it through geometry, or whether you memorize it, or whether you sort of use this intuitive thing where you think about what it would have to be if you leveled this thing out rather than inclining it, any way it goes, comes out to mg sine theta. This just being the magnitude of f sub g. All right, that looks fine, okay? And we could probably like measure the mass of this thing and measure the angle, and we would actually be able to get a number for that. And then the maximum value of the static friction, well, that's going to be mu s f sub n. Right, just from definition. If you watched the last video, you know that. And it's an equality because we're at the maximum value rather than that less than or equal to thing. But we get to this point and we realize that we're kind of stuck. Okay, and the reason we're kind of stuck is that, sure, I mean, if we were putting numbers to all this, we could pretty easily go and measure mass and we could measure theta, but what is this going to be? Okay? Well, we don't know. And so we have to somehow put normal force in terms of things that we could go away and measure, like mass and whatnot. And there's one piece of information that we have not used in this problem yet, right? We went and we took the general Newton's second law and we applied it to the x-axis, which you can always do. Well, we can do the same thing and we can apply it to the y-axis, right? We haven't used that bit of information yet. Kind of like going to the vertical direction for projectile motion if you run out of options in the horizontal direction. Pardon my writing here, this is meant to be a y. And again, this thing isn't like lifting up off the incline or burrowing down into it, so we're expecting the acceleration in the y direction to be 0 as well. And there are two forces in the y direction, just like there was in the x, except now we've got f sub n, and we've got not the x component of g, but the y component of g. And it's going to have a negative sign on it because it's along the negative y-axis as we've got it laid out over here. And so that whole thing has to equal 0. And going swiftly through it, well, this has to be mg cosine of theta. It's the adjacent bit over here to that angle. And that means that f sub n, in terms of things we might actually be able to measure, like mass and theta, is just equal in magnitude to mg cosine of theta. We can take that. We can go over here, okay, and substitute it in, right? If it's f sub n over here, then it's f sub n over here. We can put this in wherever we see an f sub n. And so what we do is we end up with mg sine theta times mu s times mg cosine theta. And that all has to be 0. You're going to notice something here, right? We've got mg's on both of these terms, and we've got a 0 over here on the right, and so we can divide out by mg, and it just cancels, 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 and just disappears. Once we've done that, we can move mu s cosine theta to the other side, leaving sine theta by itself, and then we divide both sides by cosine to get the coefficient of static friction all by itself. Now, why would we want to do that? Well, because, as it turns out on the other side of the equation, we've got theta, well, almost all by itself. So if we really wanted the angle at what angle part of this, then we just take the inverse tangent of both sides, and that gives us that expression on one side, and it gives us inverse tangent mu s on the other side. That, taking the inverse of a tangent just gives you back theta. And so theta is equal to the arctangent or inverse tangent of the static coefficient. Remember, that's the thing that is characterized by the surfaces in contact. And this is kind of interesting. What this is telling us, not not kind of interesting. This is interesting. What this is telling us is that the angle at which the box will break away isn't dependent on its mass. It's not dependent on G, like what planet we're on, okay? It's not dependent on anything except the static coefficient of friction between the box's material and surface and the surface of the inclined plane. That's a counterintuitive thing. Most people are like, oh, well, mass has to have something to do with it. You have a heavier object, maybe it breaks away more quickly or something like that, you know, in terms of inclining that thing more and more and more until it breaks away. But no, okay, at least with our simple model of friction, and as it turns out, this is quite accurate, all it's dependent on is that coefficient. That's all you need. Now, I know we've gotten to a little bit of a mess here, but usually people like to see sort of all the details and see me talking through it. So on the next slides, you're going to see sort of all the algebra come together. Okay? But it comes down to this same conclusion, though I don't know if I actually solve for theta or just leave it sort of in this form. Okay? So you can go through, lays out all that thing, you substitute across just like I did, work it down until you've got the coefficient of static friction equal to sine over cosine. Sine over cosine is just tangent, and that's where we get to the expression that we had on the last slide. This is kind of cool. If you actually do the experiment, right, like you get yourself, a board or something like that, and you put a book on it, and you tilt the board up, and you measure with a protractor what the angle is, and you wait for you tilt it up and tilt it up and tilt it up until the book breaks away and moves. Well, you need to do a lot of trials because friction is notoriously finicky in terms of an experimental quantity, right? If you get a little bit of skin oil or something on the book, then you might change the coefficient of friction a little bit, which is then change what angle it breaks away at. But in general, if you're careful and you do a bunch of trials to establish consistency, like you might be doing in the physics lab portion of this course, well, you can do that experiment. And I did a pretty sloppy job here. I think I only did like 3 trials per point here, but what I'm doing is I'm measuring angle in degrees of the incline versus the mass of this block. So I just added weights to it at each stage, okay? And then I tilted this thing up until it broke away and moved, and so that's what this angle is, the angle of breakaway is what we're looking at here on the y-axis. And you can see that if you squint, that maybe there's like a kind of a vague downward trend here, but a very slight one, a matter of only a few degrees at most, okay? And I was being sloppy. Look at the variance here, okay? What this basically shows is that there's either a very weak or no dependence at all on the mass of this block versus the amount of degrees you need to tilt it up to get it to break away. And that's exactly what this expression is telling us, which is that the theta is wholly dependent just on the surfaces that are in contact, those materials, the roughness of those materials, all of that kind of stuff. And that's pretty cool, okay? Completely independent of mass. So that's a good example of one showing this relationship, and also to show you sort of how you do a two-dimensional sum of forces problem. We're going to get into some more examples after we talk about tension in the next video, and I'll see you for that one soon.